All right, physicists, welcome to our April 7th edition of Physics. I hope you had a nice Easter break. It has been a while since we've talked. This is my wife and kids. They were very busy making all their Easter stuff. And since my wife started a job at a church, I feel like I'm there all the time. Okay, so last week we were trying to finish up our rotational dynamics unit. And so we spent quite a bit of time talking about moment of inertia, which is like gravitational mass or inertial mass, and how torque in rotational terms is like force, and we can have our F equals ma, and we can have our kinetic energy change is due to work. And so we were just taking all of our old stuff and pouring that old wine into new skins of the rotational language. And then on Wednesday, what I did in that video, we talked about rolling as a rotation plus a translation. And so the essence of it is gotten across in this picture, where you have the center of mass that's going at some speed that has to do with how fast it's rolling times the radius, and the kinetic energy of the wheel then has a rotational part and a translational part. Okay, so you have K equals your K rotation plus K translation. And there's your rotational part of your kinetic energy, and there's your translational part of your kinetic energy. And then at the end of Thursday, what we pressed on to is discussing angular momentum and angular momentum conservation, just the same way that we did momentum and momentum conservation. And in class today, I'm sorry, I don't have the film crew here to do it, but I did bring a couple of props in to do a show on angular momentum stuff. So regardless, let's just do a quick problem on rolling, and then we'll do a quick problem on angular momentum, just to make sure that we have these ideas sort of firmly in our minds. Okay, so this says we have a 1,000-kilogram car that has 4 wheels. Okay, so we have 2 different masses we need to worry about in this problem. We've got the mass of the car, which is 1,000 kilograms, and we've got the mass of the wheels. Okay, and that little m is 10 kilograms. And it asks the question, when the car is moving, what fraction of its total kinetic energy is due to the rotation of the wheels about their axles? Assume that the wheels are uniform disks. Okay, so the reason why it's important to know what the geometry is that different geometries where you have more of the mass that's spread out have different rotational inertias. In our case, for this uniform disk, you would either calculate or look up that I equals 1/2 mr squared. So if you wanted to, it asks what fraction of its total kinetic energy is just due to the rotation of the wheels. So part of that energy is just the rotation of the wheels. Part of the energy, the kinetic energy of the wheels themselves, is due to the translation. So if I wanted to write the total kinetic energy, what would it be? It would be 1/2 mv squared. That would be the kinetic energy of the car part, plus 4 times the kinetic energy of the wheels. And so what would the kinetic energy of the wheels be? It would be 1/2 I, whoops. So it would be 1/2 I omega squared plus 1/2 little m v squared. Okay, so you have a rotational and a translational part for each one of those. So we take it and multiply by 4. Now, if we want to find just the rotational part, it's just that 4 times 1/2 I omega squared. It's just this part of it that they want the ratio of take this divided by that, and that's what the question is asking. And ask, why do you not need to know the radius of the wheels? Well, let's go one step farther here. This would be 4 divided by 2 would be 2. I is 1/2 mr squared, so 1/2 mass times radius squared. But then when I want to put in my rotational speed, I need to take my center of mass speed and divide it by r. So v over r squared. And so this would be, the 2's cancel. This would just be m. And then my r squared and r squared down there cancel. mv squared. Okay, so that's why you don't need to know the radius of the wheels. It's just that the r in the angular velocity and the r in the moment of inertia turn out to cancel in this case. Okay, another homework question that I gave you for the homework that's due this coming Monday is this one. It says you've got 3 particles with different masses, and they're fastened to a rod with a negligible mass. It says the rigid assembly rotates around point O at an angular speed. Okay, so they give you a number for this, they give you a number for that, they give you a number for that. It says, what are the rotational inertia and the magnitude of the assembly, the magnitude of the angular momentum of the middle particle, and the magnitude of the angular momentum of the assembly. Okay, so for part A, by now you hopefully know how to calculate the rotational inertia of an object, because it's just this. It's mass times distance squared, and the distance that you're measuring is the distance to the axis of revolution. And so in this case it would be like md squared plus m2d squared plus m3d squared. Okay, we had a similar one that was like this earlier. The part that's a little different is just remembering what is the angular momentum. Well, remember, for a single particle the angular momentum can be written like this. If we wanted, we could even think about our angular momentum for a single particle in terms of I omega, because this would be your I for just the second, the middle particle. So the L2 would be, you know, I2 times omega. So it would be something like m2d squared times omega. So that would be okay to do. It would also be okay to use this sort of thing where you have the radial distance times the v. In this case, they are perpendicular, so the sine of 90 would give you 1. So it would just be 2d times v times m. Okay, so that's going to give you the same thing as this at the end of the day. Okay, so that's your B, and then your CS for the angular momentum of the assembly. Well, you have the I of the assembly, and angular momentum is just I times omega. Okay, now the reason we were interested in angular momentum is so that we could do problems with angular momentum conservation. In this one, the example was of a guy who's spinning around on a chair, and then he brings these weights in closer to his chest. That reduces his moment of inertia. So if the product of the moment of inertia multiplied by the angular velocity gives you a constant, if I gets smaller, the angular velocity gets bigger. So that's reflected in him as spinning faster. So I did this example today in class where I brought in the wheel, and you get it spinning, and you hand it to somebody on a chair like that, and then they turn the wheel, and as they turn it, they start to spin because you have conservation of angular momentum. The thing to be a little careful about in cases like this is that it's a little bit hard to realize that once you turn that wheel, the total person and wheel system has more kinetic energy. But that's because you're taking that chemical energy in your body and you're transforming it into the energy, the kinetic energy of the system. Okay, so today we're going to do one last topic, but it's a super important topic. And I feel like if there's two equations you're going to remember from this class, one for each set of knuckles for your tattoos, today we're going to learn the other one. So F equals ma is one of them. The other one is this one, Newton's law of gravitation. And it's this incredible idea that is a very interesting one. It says every single mass in the universe pulls on every single other mass in the universe. And in Newton's original idea of it, he said it happens instantaneously. There's no explanation for it all. It just is communicated one object to the other object at this. There's no slowing of that signal at all. Now, in the time since Newton, we have come to think about this in terms of a gravitational field. Of course, some people will want to put it in terms of space-time or whatever, but I think it's useful just to think about this as a field in space for the time being. And the way this works is this field is just hanging out in space, and if you put a particle, that particle will get pulled on by the field. If there's no particle there, it doesn't pull on anything. It's just hanging out there. And this little graphic is trying to be a visualization of what does that look like? Well, you've got a bunch of little vectors pointing down towards the center of the Earth. And those are the gravitational field vectors. And there's some gravitational field strength. And if you take the mass times that gravitational field strength, you get the force of gravity. Okay, now I'm going to take a little detour here because I think it is important to just understand the history of this subject for a little bit, because this is one of those areas where scientific understanding intersects all sorts of other understandings, like your religious or cultural understanding, things like that. And what's important to realize is that for about 1,500 years, there was a very successful and mathematically rigorous theory of how planets and stars moved. And it was made by Ptolemy. And in this geocentric model, what you had was the Earth at the very center, and you have stars that are attached to a sphere outside of the Earth. Now, it was known from very early on that the planets don't move exactly the same way as the stars. And in fact, if you have any friends who are into astrology, you will know that sometimes the planets appear to move in retrograde. They appear to go backwards from how you'd expect them to move. And so, to accommodate this, Ptolemy made a somewhat sophisticated model where instead of being attached to the same sphere as the stars out there, the planets are attached to different spheres, and they have another circle on which they revolve. Okay? And so these were the cycles of the planets, and then they would have epicycles within the cycles. And what's interesting about this is that from the modern point of view, what this essentially is doing a Taylor series in calculus, where you add on more terms, and by keeping more terms in there, you're able to improve your theory arbitrarily well. And in fact, there's no way if you didn't send out rockets or satellites out into space, there'd be no way to say definitively Ptolemy was wrong, because all of the math works out. He had this worked out really well. What changed was our point of view about things, and we honor Copernicus not because his math was better, but because he had a totally different conception of how this might work. And in his conception, the sun's in the middle, the planets and the Earth go around in perfect circles around. Now, it's worth noticing that in Copernicus's model, the math did not work out quite as well as it did in the case of Ptolemy. But we honor him because if we think it's closer to true. We think that the sun actually is something like being revolved around by the planets in the way that I'm sure you all learned in middle school. Okay, so the part here where we need to start paying attention as early physics students is in the terms of Kepler, because Kepler was the person who took that model of Copernicus where the Earth is in the center and he made it into a mathematical theory. And in his mathematical theory, he was able to devise some empirical relationships. And let's see what they are. So these are Kepler's laws. And it says, well, instead of having that idea that all of these orbits are just going around in circles, the data fits really well if we put the sun at one of the foci of an ellipse. Okay, so your Earth follows one of these ellipses. Mars follows a different one, etc., etc., etc. And the idea here is that each one of your planets moves in an elliptical orbit. Then the other one is that if you have a similar area, it takes the same amount of time. So like right here, you can see that our object didn't cover as much distance in the amount of time as it covered over here. Here it's moving more quickly, here it's moving more slowly, but they cover the same amount of area in that 2D plane. And then he makes a further claim and he says, look, we can connect the period, so that's how long this planet takes to go all the way around the circle once. The period is connected to this R, I think it's the semi-minor axis of the ellipse. So he's got a t squared and r cubed. Now this all seems a little bit random. Why are these the laws? Can we explain this in some deeper way? Well, it's not clear that you could, but given what we've set up already, you might be tempted to do it. So for instance, let's say that you have a record of how your object is moving at every point in time. So it's moving more quickly here, more slowly over there, and you know how it's moving as a function of t. So you've got a function, you've got an x as a function of t. Now, let's say that you know what the mass of the Earth and the mass of the Sun, you can make up numbers. How would you find out what Newton's law of gravitation is? Well, all you'd have to do, if you knew those things, was you would use F equals ma. And then, once you have x, this is just saying F equals the mass of the object going around times d squared x dt squared. And from this, you should be able to go from Kepler's law to Newton's law of gravitation. Now, of course, it's not, the actual historical story is not quite that simple, but the seed should be in your mind that what's important about what Newton did, he took these Kepler's laws and he realized that all of this physics that had been developed in the generation before him, so Galileo was the name that you probably should have in mind because he invented Newton's laws, basically. It's just Newton took them together and said, and what he achieved was he said, as above, so below, all of this is part of the same universe. The way that a ball falls down and the way that the moon falls around the earth are the same. It's the same forces that are causing me to be able to throw a basketball and for the moon to go around the earth, for the earth to go around the sun. And so it's this incredible simplification of what's going on, because people had all of these ideas that it might be some extra thing. In the Ptolemaic view, the sky is totally unlike what's going down, where you have this perfect set of spheres, where down here, we're hungry, we're dirty, we don't have enough to eat, blah blah blah. And so in this Newtonian picture, what you have is, if you have a mass 1 and a mass 2, well, we know about Newton's third law, so we should expect if there's some force that's acting between them, this force would be the same. You get some force of gravity of 2 on 1 and of 1 on 2. And what does it depend on? Well, the force depends on some number times the first mass times the second mass over the distance between the two squared. So there's your R, and G is some number that is small. You know it's small because in Newton's theory, we are all gravitationally attracted to each other, but you don't really feel it. It's got to be small, or else we would go, kind of bumping into each other and kind of feeling gravitationally attracted to each other. You don't really feel it very much. So that's 6.67 times 10 to the minus 11th. What unit does it have to have? Well, ultimately you want force, and you have to cancel out the mass times mass on the top. So you put kilograms times kilograms on the bottom of this, and this has meters times meters on the bottom, so you have meters times meters that you have to put on the top. So that's our units that we have on G, Newton's constant. So let's just look at a couple quick examples of this that'll help us to conceptualize this. So here's A, B, and C, 3 masses. And let's just put them along a line. Okay, so this is at XA, this one is at 0, and this one is at XC. Now it asks, what's the magnitude and direction of the net gravitational force on sphere B due to spheres A and C? Now, what you need to realize is that gravitational forces add like vectors, just like any other forces. So B and A are attracted to each other. So the force from A is pulling in that direction. B and C are attracted to each other. So the force from C is pulling in this direction. Okay? Now, how are we going to find FA and FC? Well, the magnitude of FA would be that 6.67 times 10 to the minus 11 So G times M1, so it'd be 5 kilograms. And then this one would also be 5 kilograms over, and then the R is just the distance between the two. Okay, and then you do the same thing for this. And just keep in mind, don't be scared when you get little numbers, because gravity is a pretty weak force, unless you've got a really big mass. Okay, so there's your FA and FB, or sorry, FA and FC, I guess. And then the F net, well, FC is pulling in the plus direction, and FA is pulling in the minus direction. So FC minus FA. And so you'd get an answer that's in newtons. Okay, so that's the basic idea, and you know, everything gets more complicated from there, but it's a simple idea. Now, I want you to also, this is a homework problem that I gave you on this. Notice in this problem, instead of having, it's essentially the same problem we just looked at, except instead of having them all on a line, one is above and one is to the side. So in this case, your FA is pointing up because it's attracted to, B is attracted to A, and FC is over in the to the side. So this is in the plus Y direction, this is in the plus X direction. So our F is going to be FA FC. Okay, so this is a vector, FA times I, or FA times, I guess I have these written backwards. FC should be in the X direction. FA should be in the Y direction. Okay, but that's your force. They are perpendicular to each other. And so your F net, if you wanted to find out the magnitude, you'd have to use your Pythagorean theorem. And you know, the same goes for finding that angle. You'd have to use your inverse tangent of FA over FC. Okay, so these are just two quick examples. Now, why is this so interesting to us? Well, to me, the reason that this really kind of fires the imagination is that it connects to a lot of different things. So, for instance, we've talked a lot about projectile motion. You throw something. Okay? Now, in this view, Newton had a thought experiment where he said, what if instead of just throwing something, you kept throwing it harder and harder and harder, and it keeps going a little bit farther every time, except at some point you throw it so hard it just keeps falling. It keeps missing the edge of the earth. And so every time, it's exactly as in our projectile motion problem, where it's being pulled down towards the center of the earth, but it keeps falling and falling and falling and falling. And in Newton's picture, projectile motion and orbital motion are the same thing. Okay, so all that's happening here is that you continue to fall. So satellites continue to fall and fall and fall around the Earth. The moon continues to fall around the Earth. The Earth continues to fall around the sun. The solar system continues to fall around the center of the galaxy. And so we're all in this kind of motion where it's very evocative to think about. Now, one of the reasons why this is evocative is that we've already spent a lot of time in this course thinking about circular motion. And remember, long ago we said that the centripetal acceleration is v squared over r towards the center of the circle. And we said the force is just m times v squared over r towards the center of the circle. Well, what if we just use that and we say, let's go back to Copernican thinking, where our force is just acting towards the center of the circle. What if we go ahead and say this force right here, this centripetal force, is the gravitational force? Well, in that case, I can set those two equal to each other, and we should be able to recover Kepler's law of periods. Can we do it? Let's see. Well, I'm going to say mv squared over r equals g. Let's use the same symbol for r in both. They use a little r here. Let's use a little r. So gm times big M. So let's say our little mass here is little mass, little m. The big mass in the middle is mass big M over r squared. Okay, now I can cancel out the m's on here, divide both sides by little m. And now my v for orbital for centripetal motion is just the circumference 2 pi r divided by the period. Okay, and so I'm going to go ahead and put that in here. So I'm going to have 1 over r times 2 pi r over the period squared. Remember, the period is just how long it takes to go all the way around once. And we have here gm over r squared. Okay, let's just clean this up a little bit. So if I square the stuff on the top, it's going to give me 4 pi r squared. And if I divide that by r, it's just going to be 4 pi r over this squared. So I squared all the stuff on the top, divided by r. So that's this. Squared the stuff on the bottom. Equals gm over r squared. Okay, and now let's just rearrange a little bit. Let's multiply both sides by r squared, 4 pi r cubed, and then divide both sides by gm, and then multiply both sides by the period squared. And look, there I go. I have Kepler's law of periods. So, just to say it again, it takes a little work to get all the way there with all the ellipses and stuff if you're interested in doing that. But the basic idea is this very simple form of a law can reproduce all of the things that Kepler got out just by looking directly at the data. And so this is a very powerful physical model that helps us to think about a lot of different astrophysical situations. So, for instance, here's sort of an extreme astrophysical situation. You've got neutron stars, supposed to be very dense. They have a radius of about 20 kilometers, so they're very dense, very small, and they rotate very fast, 1 revolution per second. Okay, so in this case, the omega would be 2 pi radians per second. And it says, if such a star has a radius of 20 kilometers, okay, so r would be 20 times 10 to the third meters. What must its minimum mass be so that the material on its surface remains in place during the rapid rotation? Okay, so what must its minimum mass be? Okay, well, we know that the centripetal acceleration has this form. And so it must be a case where the centripetal acceleration has to be at least equal to the gravitational force, or else it'll start flying off. So we could have a test mass on the surface there, mv squared over the r would be the radius of the planet now. Okay, that's the same as this r, so let's just use a little r in here. mv squared over r equals g little m, that's the mass on the surface, big M, that's the mass of the neutron star, over r squared. Okay, and it asks what must be the minimum mass. So there's this, sorry, this looks like a V now, this is an R. Well, okay, so let's solve for the mass. The M would be V squared R over G. I think that's right. Okay, so G here would be Newton's constant, that very, very small number. That will give you a very big mass here. And remember, your V is going to be the speed of the surface, so that would just be omega times R. Okay, so you just stick in the numbers. And the only thing to be afraid of in this type of problem is that you're going to get sort of extreme answers. Stars have very, very big masses. And that's necessary to cancel out this very, very small number and get something that's reasonable. Okay, so that concludes the types of problems that you're going to get in this unit. All right, so with this sort of thing, you should be able to start working on all of the different homework problems that are due this coming Monday. The homework assignment is pretty long, so I would, if you haven't started on it yet, you definitely want to start on it ASAP. All right, so what are our big ideas here? Newton connects Earth physics to astronomical observations with his law of universal gravitation. The law of universal gravitation predicts that every object in the universe is attracted gravitationally to every other object, and the law of universal gravitation allows orbital periods and speeds to be accurately predicted. So that connects this sort of centripetal force with a direct type of force that you can measure in the laboratory, this gravitational. Okay, so I like this stuff. I hope you do too. Thank you for watching, and please start working on your homework and try to come up with some questions for Friday.